Okay, so today's lesson is about trigonometric functions. So we're going to take the derivative of sine and cosine. And let's start with the derivative of sine. Now, if you have already thought about rate of change in the context of trigonometric functions, then, and in grade 12 you learn about radians. You know, let's just look at what happens when you take the derivative of sine with degrees, right? So so if you look at what I have in green, okay, it starts at 0, 0, it goes up here at 90, and then 180, and 270, and then 360, right? And it completes its, its cycle by that point. Now, what's kind of strange about this, of course, is the derivative looks kind of just like a flat line. Now, it's not actually a flat line. It is, if you zoom in, you notice that actually the derivative has the graph of cosine, right? It starts at its max. At 90, it's in the axis. At 180, it's down at the min. And then it's sort of back to the axis and back to the max at 360. So the graph of the derivative of sine is like cosine, except kind of like last unit, or last lesson about e, it needs a correction factor, because you can see that the amplitude is clearly not equal. The amplitude is some very small number down here, 0.016 or something like that. So you need some kind of correction. So we could say something like the derivative of sine is the derivative of sine is cos times a correction factor. Now, it turns out that if you change the period of sine, right? So let's change the period, and what we're going to do here is we're going to multiply. We're going to put a k value. Okay, so we're going to put a k value in there. Let's get rid of this degrees sign, and then I'll show you what we're doing here. So if I change the period, right? So let's just look at this from a distance. The waves start to get closer together. And if you change the period enough, I say that and then I've zoomed out too far to actually fix it. Okay, so I'm going to continue to change the period. And if I change the period by the exact right number, something interesting happens where the green is my sine curve. You see it starts at 0, and instead of finishing at 360, it finishes a little bit past 6. And now my red curve is a perfect cos curve that has the same amplitude that finishes at the same time. So just like how when you took the derivative with e, it was easier because you didn't need a correction factor. The same thing is true here when you take the derivative in radians. You don't need a correction factor when you're doing it in radians, and this becomes clear if I let this sort of, you can see both of my graphs complete at exactly 2 pi. And my derivative also completes at exactly 2 pi. So if you choose radians for your measurement, your derivatives are much easier because there's no correction required. Instead, the derivative of sine is simply cos, right? And so the first thing to understand here that's really important, I'll let you fill this in if you're interested, but I don't really think you need it. The derivative for the function sine is cos x. Now, as long as, let's just stipulate that as long as x is measured in radians. And by the way, for the calculus portion of our course, we are always assuming, unless we're told otherwise, that it's in radians. So everything is in radians unless it explicitly asks for degrees. Okay? So this relationship, sine is cos, is true as long as it's measured in radians. If it's measured in radians, it's perfect, right? If it's not measured in radians, if it's measured in any other number, right? Like again, 57.3 is like how many degrees, what you'd have to compress it down to get from 180 to 2 pi. If you go any higher than this, so let's say, oh, sorry, that's way too big. If you go any higher than this, so if you measure it higher than this, now the cos is too tall. If you measure it any lower than this, the cos is too short. Okay, so the perfect way to measure these angles, okay, is at exactly this specific value, where where it's measured in radians. So all you really need to know about this is, why do we not use degrees in calculus? And the answer is, if it's measured in radians, then this statement here is true. Okay? If you're not doing it in radians, if you're doing it in degrees, then look at what GeoGebra says is your derivative. So let's just go back and delete everything here. Just make a new one. And if I say that f of x is sine x, and then I say degrees, okay, so you can see it now. It takes 360 for me to complete my revolution. The derivative of this is 1 over 180 pi, and then cos x degrees. So if let me just draw this. So pi over 180 times cos x degrees. That would be the same thing as what it drew. It's converting it to radians for us. I want to leave it in degrees, but okay. So you can see those two functions are the same. So it's like it's right, but it's compressed vertically by this really small number, pi over 180, right? And so if you want to actually make it the same height, right? If you want to actually get the correct derivative, you need to pull that 1 over 180 out using the chain rule, and it comes to the front. Now again, the special case where this does not happen is when you measure it in radians in the first place, and then when you take the derivative of h in radians, you can see the derivative is much simpler. Again, it kind of looks funny because it's so much. Let's get rid of our degrees work here. And now the relationship is perfect, right? So that idea is really, really important. Now you might think that because the derivative of sine is cos, then it would work the other way around. But of course, just looking at this quickly, you'll realize that's not true. Let's look at cos, and let's have a point called A. So let's make a slider that goes from, let's say negative 2 pi to positive 2 pi. And we'll say it's in increments of pi over 60. Okay, so I got this number here. And then I'm going to graph a point called A, h of A. So not h of A, h prime. I want the cos. Alright, so here we go. So here's a point along the cosine function, right? Now let's track its slope. So let's draw slope, tangent, point A, function h prime. Okay, so you can see right there the slope is 0. Down here the slope is 0 again. 0 again up here, and so on. Let's trace the derivative. Okay, I'm going to make another point called B. It's going to have the x value of A, but as a y value, it's going to have that slope. Okay, so right now it has a positive 0.5. Now when you trace this, let's trace it. Again, the derivative is definitely a perfect trigonometric function. However, it is not sine, right? It's not sine, because remember, sine is this one. It's negative sine, right? It's this red one, but flipped over. Okay, so the derivative of sine is cos, but the derivative of cos is negative sine. Okay, so again, the derivative function for cos f prime of x is equal to negative sine x. Again, x is measured in radians. Okay, so sine becomes cos, but cos becomes negative sine. Okay, so with that now, we can now do a couple of things. So let's make a quick table here. So let's take the derivative of a chain rule. Now remember, a chain rule is very, very straightforward. A chain rule says, so let's write the chain rule again. So let's write it out. F of x is equal to g of h of x. Okay, so an outer function and an inner function. In our case here, the outer function is sine x. The inner function, right, the inside function is 3x. Now, you know how to do this. The derivative of sine is cos, and the derivative of 3x is simply 3. The chain rule says that the derivative of f would be g prime of h repeated and then multiplied by h prime. So let's do that. The derivative of f would be g prime, so that's the cos function, but the argument is h of x, so I plug in h of x there, and then I do h prime of x and I get 3. So f prime is equal to 3 cos 3x. So how do I take the derivative of this? Sine becomes cos. The argument is copied out exactly as it was, and then you take the derivative of the argument. Okay? So again, let's just quickly do this one. So if I take sine 3x, and then I go derivative, it goes 3 cos of 3x, right? So again, these ones are not going to match each other anymore because there's an argument. You're going to have some kind of, stretch or whatever. Okay? So that's a really good question. Let's do the same thing here. So I'm going to take the derivative of the outside function, so y prime. I'm going to do it in one step this time. The derivative of the outside function is negative sine. Okay, now I copy the argument exactly as it was, and now I multiply it by the derivative of the argument. Okay, again, let's check this one. So cos 2x squared plus 1, take the derivative of g, I get negative 4x, okay, which is what I have. Of course, I wrote it a bit differently, but let's write it the way they wrote it. Negative 4x times sine of 2x squared plus 1. Okay, and that's what GeoGebra is saying as well, sine of 2x squared plus 1. Okay, so that's how you do the derivative with chain rule. Okay, it's kind of like e, except if this was e, this cos would still be a cos. In trig, the cos becomes a negative sign, and the sine becomes a cos. Okay. Okay, a couple more derivatives here. So let's try. This is just for the chain rule. So the derivative of sine of f of x. Okay, so what if you have a function inside sine? Sine becomes cos. F of x does not change, and then you multiply by f prime. Okay, so that's how that's done. I'll just put multiply. Okay, that's how you do the chain rule with sine. Now with cos, the outside function is negative sine. You copy the argument, and then you multiply by the derivative of the argument. Okay, so those two things there, really, really, really important. How do you do the chain rule with sine and cos? Okay, so for the rest of today, we just have a bunch of these. I'm going to go through them now. Of course, if you would prefer to do them on your own, that's totally fine. You can just check the page when you're done, or fast forward it or something. But let's go through these ones now, and we'll just walk through how this is done. So this first one, y prime is going to be, okay, the derivative of 2 to the x is 2 to the x times the natural logarithm of 2 times the derivative of the exponent. So it's that. Now 2 sine x becomes 2 cos x. Negative cos 2 pi. Well, cos 2 pi is a constant. Cos 2 pi is just a number, right? So minus 0. You don't need anything there. So to clean this up, we get y prime is equal to 2 to the x times natural logarithm of 2 plus 2 cos x. Again, quickly to check this one, let's just type it out. 2 to the x plus 2 sine x minus cos 2 pi. And you notice it changed cos 2 pi into just 1 because that's what it is. And the derivative is 2 to the x ln 2 times 2 or plus 2 cos x, right? Okay. Let's go through a couple more. Y prime here, okay? We take the derivative of the outside function and copy the inside function. The derivative of sine is cos. Copy the inside function and don't change it. Now I multiply by the derivative of the inside function, right? Which is 3x squared in that case. Now here, this one's a little bit different. This time, right, sine x equals the inside function, and x cubed is the outside function. Because what's happening here is that you're taking sine x and then cubing it. If you're not sure what this means sine x times sine x times sine x. Okay, that's what sine cubed x means. Okay, so this time sine is inside, or another way you could write this is you could say sine x all cubed. Okay, so the outside function is cubed. So do the derivative of the outside function. The derivative of the outside function says bring the 3 in front, copy the inside function out, drop the exponent down to a 2. Then multiply by the inside function's derivative. Okay? That's a good one to do. The difference between B and C, really important. Right? Why do they give different answers? How are the answers similar? But how, and then in another way, how are they not that similar? Right? So they're both chain rules. They both involve cubed and sine, but the order makes a difference. Okay, here, now this time we have a triple chain rule, right? So if you want to imagine, let's do a full chain rule workup of this question. Okay, and let's do it in Leibniz notation just to remind us how that works. So dy dx is equal to, okay, let's call them, so let's make a few substitutions before we start. So first of all, let's say u is x squared minus 1, okay, and therefore what we're actually doing is y equals cos to the 4 of u, right? And now let's say, let's make another substitution. Let's say r is equal to cos u. Then actually y is simply equal to r to the power of 4, right? So let's just go through that one more time. The inside of the inside function is x squared minus 1. The middle function, if you like, is cos, and the outside function is raised to the power of 4. So what we're looking at in this question is we're trying to take the derivative of y and given a couple of substitutions. Now, let's go through and do this. We know that dy dx, dy dx is going to be equal to, okay, is going to be equal to, sorry, I just had a recording problem there, dy dr, so what's the derivative of y with respect to r, times the derivative of r with respect to u, times the derivative of u with respect to x. And notice, how do I remember how this works? The drs, you can kind of think of them as canceling, the du's kind of cancel, and then you're left with just the dy over dx. So let's go through and find those three things. These things are very easy to find. Let's look for dy dr first. So I'm looking at this equation here. dy dr is simply 4r cubed. You know how to do that, right? Okay. Now let's go to this one. R is equal to cos u. So what is dr du, right? Would be change the cos to negative sine and then put the u. Negative sine u. Okay? Now what we're going to do, and then we'll do to the very top one here. Sorry. This is kind of a messy solution, I apologize. Du dx is just 2x. Like, you know, that one really is really simple, right? So now let's just look at my equation one more time and just fill in what we know. Dy dr, okay, was 4r cubed. Dr du was negative sine u, and then du dx was 2x. Okay? Now, of course, I don't want to leave r's and u's in my answer because they are, you know, everything should be in terms of x here. So let's replace r with what we know r is equal to. What was r equal to again? It was equal to cos u. So I'm going to type cos u. Okay? Then I'm going to go to the next part, sine u, and then a 2x. Now the sine u I have to replace, right? So just think about this. I don't want to leave u's in my answer. So let's go make another step. Both the u's need to be replaced. What is u equal to again? X squared minus 1. So I go here, I go x squared minus 1, and I go here, and I go x squared minus 1. And I got to make sure that stays in a bracket. Okay? And there you go. It's a triple chain rule where you've managed to, just use your Leibniz notation and keep it relatively simple. So let's summarize here. The substitutions we made, we took the very inside function and called it u. We took the middle function and called it r. And then we took the outside function and just left it as y. The three derivatives are the derivative of each one in terms of its substitution. And then at the end, you just replace everything back with what it had. Let's go to GeoGebra and just check our work on this one. So again, we have cos, so let's say cos x squared minus 1, okay, is that. And then all of this is to the power of 4. And then we want to take that derivative. It's interesting looking. This is going to, okay, never mind. Okay, so let's look at what it came up with. So it has a negative 8x. Okay, you can see where that's coming from. The negative is here. The 2x is here, and then there's a 4 there, right? So they can clean it up a bit. So let's go dy dx. Negative 8x, I can see that. Now, what do I have left? I have cos x squared minus 1 cubed. Okay. And you do too much math for your computer to handle. I wonder how much of that it saved. Down to the last second. Okay. All right, so I have that. And then what do I have left? I have sine x squared minus 1. And that's it. Right? So let's look at what GeoGebra said. They have a negative 8x, a sine x squared minus 1, and then a cos cubed x squared minus 1. Sorry, I wrote this cube. I wrote the cubed in two places, right? I wrote it. It should be in one or the other. You don't want to write cubed in both places. I think it's generally a better idea to put... I would say let's get in the habit of writing the cubed here, because it's just easier to read when it's sorry. Okay, so sorry. This needs a space, and then this needs to be x squared minus 1, and then this needs to go. Okay, and actually you don't even really need the bracket then if you do that. Okay, so that's kind of I think that's a nice way of writing it. This means the final thing is cubed. So you do cos of x squared minus 1. And then you cube the result. Okay, let's do this one in Leibniz notation as well, just to get the hang of it, just to keep working on this a little bit. Let's say y is equal to cos e to the x. I'm going to say u is equal to e to the x, and therefore y is equal to cos u. Now dy, derivative of y with respect to u is really easy. I change it to negative sign, right? Cos becomes negative sign. Very simple. Now I'm going to go, what's the derivative of u with respect to x? Well, e to the x is its own derivative, right? So to get from here to here, all I'm doing is just taking the derivative of e to the x, which is itself. Now the derivative of y with respect to x is the same thing as the derivative of y with respect to u, multiplied by the derivative of u with respect to x. So we simply replace those things with what we want. Dy dx is equal to... Okay, dy du I said was equal to negative sign of u, and then du dx is just e to the x, and then I'm just going to replace u with what I know it to be equal to, which was also e to the x. Now again, do you need to do Leibniz for this one? I don't think so. You don't need to do Leibniz for this one either, but I do think it's a good habit to be in. It just makes this work. If you know your Leibniz, then you're never doing more than one thing at a time, and you'll probably cut down on your mistakes. Okay, now this one is a product rule, so I don't know if Leibniz notation is all that useful for product rule. Probably just as easy to do prime. So let's say f of x is equal to g times h, and therefore f prime is equal to g prime times h plus h prime times g. Okay, and we'll just find all the parts. So g of x is x squared, then g prime of x is 2x. then h of x is sine x, and h prime of x is the derivative of sine is positive cos. It doesn't change signs. So the derivative of f, right, would simply be g prime, which is 2x, times h, which is sine, okay, plus the derivative of h, which is cos x, times the derivative of g, times the original g, which is x squared. Now, factoring these ones doesn't work quite the same way that it did with exponentials, because sine and cos often cannot easily be factored. However, you can factor an x here, in which case you get 2 sine x minus x cos x, right? Would be a way to factor that one. At least now you could look at this and say the derivative is 0 when x is 0. Now, solving the inside is not going to be so easy, right? It may not even be something we do, but you could definitely tell me that there's, like, if I could ask you, like, verify that this function has a critical point at 0, you could do that, right? Because you could take the derivative and then show that a value of x makes the equation 0. Now, as for the rest of the equation, 2 sine x minus x cos x. Oops, I guess it doesn't know how to do that. It's possible we might be able to use some identities or some substitutions to figure this out. Like, we could divide everything by cos, for example, and we get 2 times sine x over cos x minus just x. And that you could solve, because that's 2 tan x minus x, and therefore tan x, I'm not even sure you could solve that. I don't want to go too far down this rabbit hole. It's possible it can be done, and I'm just not thinking of how, but it's probably not something, that's definitely not something I'm going to ask you to do. I think this question would be more something like verify that 0 is a critical point. Okay, I think, you kind of get the idea. I'm going to leave the rest of them for you. I'm going to open up a discussion area, and I'd like someone to post. And again, you can view that post and, of course, ask questions or show me what you tried or how you did it. Basically, the only thing to today is just getting these things done. So give them a try, and feel free to pose any questions that you want.